Two students are studying the interference of light, and they use a laser of wavelength 580 nanometers. So that's our wavelength. What's the energy in electron volts of one photon of light from the laser? Show you working. Okay, because we've been given the wavelength, the two formulas we have for energy of a photon, E equals hf and E equals hc over lambda. We're going to use this one because we've got lambda. There's two ways of doing it. I'm going to do way 1 over here and way 2 over here. See, hopefully we get the same answer for both ways. Alright, E equals hc over lambda, which equals 6.63 by 10 to the minus 34 by, so that's Planck's constant, that's what h is. C, speed of light, 3 by 10 to the 8. Now these are in the formulas page of your exam book, and they possibly are also in a cheat sheet if you wanted to write them in there, but they're definitely in your notes somewhere. Now 580 nanometers is 580 by 10 to the minus 9 meters. Okay, you can't just write 580 in there. So when you work that out on your calculator, you get 3.43 by 10 to the minus 19 joules. That's the unit for energy. From here, we have to put it into electron volts. So to go from joules to electron volts, we divide by 1.6 by 10 to the minus 19. And when we do that, we get 2.14 electron volts. The other way of doing it is the same formula, E equals hc over lambda. You'll notice in your formulas page there's two values for Planck's constant. There's this one and there's the other one, which is 4.13 by 10 to the minus 15. This is the one we're going to use, and if we use this in this formula, the answer we get out is directly in electron volts. So 4.13 again by 3 by 10 to the 8, because the speed of light hasn't changed and the wavelength hasn't changed either. 580 by 10 to the minus 9. You put that in your calculator, you get straight to 2.14 electron volts. Okay, so it depends on which Planck's constant you use. If you use the 6.63, the answer you're going to get is joules, and then you have to transfer it over. If you use the 4.13 by 10 to the minus 15, the answer is straight away in electron volts. Okay, just make sure you know which one you're using. Alright, that's that one. Question 4. Alright, carry on from that. Just remember that the wavelength is 580 nanometers. They set up two slits. Here's the laser, two slits, and you get interference pattern is shown. This is the same interference pattern. C is the center, which is a bright band, which is good. Right, X is a bright band, they say, and Y is a dark band, the one next to it. The path difference to X, to here, is 1160 nanometers. What's the path difference to Y? Show you working. Well, the path difference at the middle is equal to 0 wavelengths. The path difference to the next bright band is 1 wavelength. The path difference to X is 3 wavelengths. The path difference to this one here is half a wavelength. So 0, half. This is 1. The next dark one is 1.5. The next, oh, I've got that wrong, haven't I? The next bright one is 2 wavelengths, and the next dark one must be 2.5 wavelengths. Now they've given us that the path difference to X is 1160, and if you know that's 2 wavelengths, so if you put the two 580 nanometers in, you get 1160. So it's not really any new information there. What we want to know is the path difference to Y, and that's 2.5 wavelengths. It's 2. The 0.5. So working for this one, for 2 marks, is path difference at y is equal to 2.5 wavelengths, which equals 2.5 times 580 nanometers. Calculator gets me 1450 nanometers.